what I was trying to, and I didn't do it very eloquently, I was trying to ask you, like, did you see this in class?
Yes.
And that's like the basis of everything that we are doing. So I'm not sure how much of a shortcut you were given or told that there's a shortcut, but like I'm gonna grab question 3 from 8.6 and show you like what you're going to be asked to do.
Okay.
So here is, can I get away from that? There it is. All right, so here's question 3. And you can see that it's really close to the right-hand side here of this. See how there's this and there's this, they're
Right.
really similar.
Yep.
To make them the same here, x has to become minus x. If this x here becomes minus x, then it's exactly the same as this. Do you agree with that?
Yes.
Okay, so what you do is you take this power series and instead of this x up here, you replace it with minus x.
All right.
And like the show's over. I mean, that's it. And then, I mean, you have to simplify here, but in terms of like what they're asking you to do here, that's the first thing is to determine the power series. And then we'll talk about the interval of convergence for in a moment, but you figure out how you can get back to like, how is this different than the original? And then you get then you substitute your x back in and then you simplify. So this one, you know, it's not great. It's minus 1 to the n, x to the n is one representation of it. Something like that you might see. And I don't know, did you see any examples like that in class?
Not one like that simple. I need to.
Okay, we're gonna do more complicated ones, but that's your starter one.
I'm gonna run out to my car really quickly.
Sure, just let me know when you're back.
All right. Thanks. All righty.
Okay, so you're back.
Yep.
All right. So the original power series, and this is important too, the original power series, the one that's given here, is it converges if the absolute value of x is less than 1. Okay, you probably saw that in class.
Yes.
Okay, very important. So whatever you change it to, that also needs to go in here. Okay, and that's how you deal with the convergence part. So we've rewritten the series, but then you take the absolute value of negative x, and that has to be less than 1. And the correct way to do this is you break it apart as the absolute value of -1 times x, absolute value of -1 times the absolute value of x, and you get just the absolute value of x is less than 1.
I'm with you.
Okay, so let's look at another problem here, something slightly more complicated, and see how the understanding goes here. I guess we'll just go to 4. I mean, I do feel like this could be helpful to go incrementally, but this is way too easy. We can jump to smarter ones. So here's 4, and you look at your original. Your original is 1 over 1 minus x. Okay, and so if this over here is sigma x to the n, Okay.
Uh-huh.
Well, it looks like x goes to 4x squared.
Right.
Okay.
And
And
then
then
you need to
there's a
multiply it by 5
right.
as well.
So how does that affect? So you take your sigma, and instead of x, you put in 4x squared to the n,
Mhm.
and then your 5 goes on the outside here.
Right.
Okay. So then depending on how much simplifying you need to do here, this is 4 to the n, x to the 2n, sigma, and then a 5. You could bring the 5 in, and then you do need to say 0 to infinity. And that's usually the easy part. And then it's the convergence that's not so easy. So it's absolute value now of 4x squared less than 1.
Okay. So basically you just take whatever you're doing to the x
Yes.
and just yeah, okay.
Yes. It gets more I mean, that like 5 gets a little more complicated, and same with, I mean, they all have different things. You basically are manipulating this original thing to like somehow get back to this. Like it's
Right.
really 5 times, this, and then x really goes to 4x squared. Like that's, but there's other things that can go on, and we'll cover a few of those here. So this is the absolute value of 4 times the absolute value of x squared less than 1. You divide by 4, absolute value of x squared is less than 1/4. And then you got to take a square root. So x is less than square root of 1/2. Okay, I'm sorry, 1/4, which is 1/2. Sorry, messed that up. Okay, so your x has to be less than 1/2. Let me know if any of this is unclear.
I understand. Yeah, I get it.
Okay, all right, so let's keep going here. Let's do
So then the interval of convergence will be negative 1/2 to 1/2.
yes.
Okay.
And depending on your instructor, you gotta be really careful with how how you do that. You gotta maybe label it.
Yeah, she usually likes it like that.
The radius of convergence is 1/2.
Right.
That's usually the first thing you write.
Right.
I mean, I mentioned this a few times. Like I really get sloppy in this part of calculus because it's a little bit different.
Uh-huh.
Okay, so this one is more problematic. It's 2 times 1/3 minus x. Okay. And a
Mhm.
lot of times students are, what do I do here? Well, you actually have to factor out the 3 on the bottom. So it's 1/1 minus
x/3.
x/3. Okay. And so that part in front's easy, but now x goes to x/3. So when you write it, it's sigma x/3 to the n, and you got a 2/3 here. So, and n equals 0 to infinity. Some instructors index this differently. Just do whatever they do. So this is x to the n over 3 to the n. They do kind of want you to clean it up. So do you see how there's a 3 on the bottom here? That
Yeah.
can multiply in. So this is probably how I would present it if I were a student. To x to the n over 3 to the n plus 1. Because bases are the same, you add the exponents. That's probably how I would show it, like that.
Okay.
And then again, you got to take this part over here, this x/3, put it in absolute value less than 1. And you don't really need to show work, but this is the work that you would show if you really wanted to.
Uh-huh.
So the radius of convergence is 3. The interval of convergence is -3 to 3. You would need to check the endpoints to know if you change those to brackets or not.
All right.
Let's look at 8, since 8 is not in the back of the book. If you're okay with it, it's got a couple other little wrinkles in it
All right.
that are different than other ones. Okay, so again, like I noticed there's an x 1/, And I'm gonna switch the order here. So it's 1 plus 2x squared. And like what we're trying to remember, we really want 1 over 1 minus x. So this x goes to minus 2x squared like that. So it's sigma, and you can't put x's on the outside. So the x has to actually come in here. Minus 2x squared to the n, that's the x to the n part. And now it's a matter of simplifying this. So what I see is you almost always treat the -1, you write it as -1 to the n. And then you have a 2 to the n. And then you have an x to the 2n, but then you have an x to the 1 here. So it becomes x to the 2n plus 1 like that. This is a little bit difficult for instructors to grade. So I mean, there are a number of different ways that you can do this. And then in terms of your convergence, you take this minus 2x squared absolute value has to be less than 1. I think that's how we do it here. I may want to check this one because of the x in the numerator. Let me just double check that. All right, convergence. Well, I'm not finding any examples, so we'll just go with this. So it's absolute value of 2, absolute value of x squared less than 1, absolute value of 2, x squared less than 1. So x squared has to be less than 1/2. And then you take a square root of that. So it's absolute value of x less than square root of 1/2, which is square root of 2 over 2 when you simplify. So that's your radius of convergence. The way I check these, because I forget to do this because I don't do it very often anymore, is I actually take this number here and I put it back in the original, and it should give me 1. Like 2 times the square root of 2 over 2 squared. That should equal 1. That's
All right.
like undoing it. So this is 2 over 4, and that does work. And so but you can't do that. You have to show your work to get this. And then your IOC would be minus root 2 to root 2 over 2. Did you do any Taylor series?
Yes, we just did that.
You just did that. Okay. Oh,
Well, I understood those more than I understand.
Oh, good.
I understood.
Good.
I'm still starting to make more sense now.
Okay, so let's go back to your pictures here.
What number did we just do?
8.
Okay.
8. 9 and 10 are a little odd. I'd have
Yeah,
to
you
think.
can skip to 11.
11.
Yeah, like 11 through 18 is what she listed on here for us to.
Okay, so 11 is the start of like, you kind of gotta, it's not just, oh, put the number in, put the X in. You have to like manipulate this thing before you do it. So like it's what I call non-obvious. And for example, here, like the bottom factors to x minus 2, x plus 1. And you're going to use partial fraction decomposition to separate it. Okay, so that's x minus 2 on the bottom, x plus 1 on the top. Okay, and the we're trying to get 3. So you could write like your A and your B here. Did your instructor ever go through a faster way to do this with you?
I don't remember.
Okay.
But I remember this.
Well, the slow and steady way is to label it A and B, and you cross multiply, and you create a system of equations.
Yeah, that's how we did it, but
There are faster ways, but I won't do that here. So that's plus B x minus 2. Okay, and 3 equals that. So you have 3 equals AX plus A plus BX minus 2B. So 0x equals AX plus BX. That's one equation. And really it's 0 equals A plus B, because you don't need to write the X's.
right.
So A equals minus B. And then in the other equation, that's where you actually use the number 3 equals A minus 2B. Since A equals minus B, you sub that in, minus B minus 2B minus 3B equals 3. So B equals minus 1 and A equals 1. So why is that important? Well, this thing that we started with up here, this f of x, let me actually rewrite it here. This f of x is rewritten as equaling 1 over, that's the A, 1 over x minus 2 plus minus 1 over x plus 1. Okay, and then these are both power series. So let me kind of rewrite it here. It's 1 over negative 2 plus x plus negative 1 over 1 plus x. So on the right is probably the easier one to write. X goes to minus x. Okay, and then you got a negative out in front. So it's sigma with a negative out in front minus x to the n equals 0 to infinity.
Right.
Okay. And there's a lot of things you could do here potentially to like simplify it, but we'll write it this way. So this negative out in front, it doesn't cancel with that. I mean, some of them it cancels it. You could reindex it, but it probably just better leave it minus. This one's the more awkward one. So you want to actually move this negative up to the top. So if you move it to the top, it's the equivalent of like factoring out a negative on the bottom. Let me do that first. So if you factor out a negative on the bottom, it becomes 2 minus x. And so that negative comes up here. And then you also want to factor out a 2. So you get 1 minus x over 2. And you can see here, you got a couple things going on. You got that minus 1/2 now out in front of your sigma.
Right.
And then x goes to x over 2. So you have x over 2 to the n. And so you got boy, you got a lot of mess here. Sigma x to the n over 2 to the n plus 1, because I'll combine it with that one. And then you got a negative out in front, minus sigma minus 1 to the n x to the n, like that. Then you got to find the interval of convergence.
Or is that second part? That part right there is that are you subtracting it from the left, from the one on the left?
Yeah, yeah.
Oh, okay.
Like these are separate things.
Oh, okay. I see what you're doing. You just moved that one down. Okay.
Yes. Now, the interval of convergence, radius of convergence, you get from looking at kind of each one and deciding like which one is more restrictive. So see, the one on the right went to negative x. So you do absolute value of negative x less than 1, which is absolute value of x less than 1. So that's fine. But the one on the right was absolute value x over 2 less than 1. And that's the 1/2 absolute value of x less than 1. So absolute value of x is less than 2. So this one is more restrictive. So you would use that.
Okay. All right. This is making a lot more sense than it did.
Great. 12 is more complicated, but it's the same type of problem. It's partial fractions. decomposition, and you just do it and see what's going on there. Would you like us to do 12?
Let me see. Got it. Is it a complicated one?
Yeah, I would. So what I would do, like if I were practicing, I would put it into a tool to do the partial fractions decomposition and then practice the power series. But we can do it if you'd like.
So, okay, I think the part that confused me the most for these type of problems is we had a theorem that says if the power series sum of c sub n x minus a to the n has a radius of convergence greater than 0, then the function f of x defined by the series is differentiable.
Yeah, that's like a 13A type of problem.
Okay, can we do something like those? Because I didn't understand those at all.
Yeah. Okay. So 13. All right, so like with 13, what you're supposed to start with is you're supposed to start with, okay, and I'm going to come outside here. So sigma x to the n equals 1 over 1 minus x, okay? So if you take the derivative on the right here, and this is kind of your derivative notation, the derivative is, and it's kind of quotient rule, but like, and this is going back, you can also look at it like this, so it's power rule.
Right.
So the derivative is -1, 1 minus x to the minus 2 times the derivative of the inside, which is -1, which cancels with that. So you end up getting 1 over 1 minus x squared.
Why do you need to take the derivative of it?
Well, you'll see in a moment.
Okay.
So now we're going to take the derivative of this, okay? And they're mathematicians long before I ever came to existence, or both of us did. They figured out that you can just ignore the sigma and take the derivative. So this is sigma n x to the n minus 1. You can just use power rule on this.
Oh, okay.
And they're like, there you go. Okay. So how does that help you? Well, what you could do is in your problem, if you recognize that this is the derivative of, so let's say you started with 1 over 1 plus x and you take the derivative of this. Okay, its derivative is 1 over 1 plus x squared, but there's actually a negative here. So if you want to make it like this, you have to put a negative here to make it positive there.
Okay.
And if you don't believe me, I mean, you can work through that, but that's how it works. Okay. So, well, what is the power series for this thing on the left? Well, it's negative sigma x goes to minus x to the n. Okay. You can bring this negative inside here, so it's sigma minus x to the n, and then you can just take a derivative of this. Okay, so the derivative of this is bring the n down front, minus n minus x to the n minus 1. Take the derivative of the inside function, which is minus 1, and then you can combine some things, so you get n minus x to the n minus 1.
Okay.
And so the point is that you can do a problem like this by figuring out what it came from, and then taking the derivative of that one that it came from.
Okay.
So we should do another one to kind of make that clear. But that is
I understand what you're doing.
Yeah, it's like, how would you know to do it?
Right. Yeah.
Yeah. Okay. let's try. So how do we want to do this again? It's like I almost have to start again. I have to start kind of from this 1 over sigma x to the n is 1 over 1 minus x. Okay. And then the derivative of this, like we got to start there. The derivative of this, let me just go grab it, is 1 over 1 minus x squared. And that's n x to the n minus 1. We have to start with like an understanding of that. Okay. So like, again, like a more basic problem is I want to know, well, we kind of already did that. Well, so let's keep going. Well, no, that's no good either. Let me see if Lamar here has a better example of this. Yeah, I mean, they just do that. All right, let me go back to your problems. Okay, well, let's just go with let's just say your problem was -1 over 1 plus x squared. Okay, like they want you to figure this out right here. And so what you would have to try to do is realize like, okay, well, it's not this, but maybe it came from something like this. So you would go back to 1 over 1 plus x, and you would take a derivative of this. Okay, and you would see that your derivative is -1 over 1 plus x squared when you take the derivative of this, and you realize, oh, well, so the derivative of this gets me to this. So you're like, well, you ask yourself, what is the power series for this? Okay, and you realize, oh, it's really similar to, well, it's 1 over 1 minus x, but x is now minus x. So the sigma for this is x to the n. So the sigma that you care about is minus x to the n. And since the derivative of this, a derivative of this thing gets you to the one that we care about, you want to take a derivative of this thing over here. And so you just take the derivative of the inside function, n minus x to the n minus 1 times -1.
Okay.
It's not obvious.
Right.
Let me see here what else I can say on this topic. Let's look at maybe part B.
Okay.
Maybe this should probably be the last. I mean, because we also need to do the integral to go the other way to like maybe make that clear also, which isn't great. Okay, so we got to figure out, well, what does this come from? So we look at the bottom, and when you take derivatives of fractions, rationals like this, you know the bottom really doesn't change. So we say, well, what if it's what over 1 plus x? Okay, and we take the derivative of that. We know the derivative of that is -1 over 1 plus x squared. Okay.
Right.
And then when we take the derivative of this, okay, it becomes 2 over 1 plus x cubed.
Like, why would you take the second derivative?
Because we got to get to the cube. I'm looking at that.
Okay.
That's how I'm like, and it like, this is not obvious. This isn't like, oh, you should know this. It's like, you have to be told and shown this, like, to know this. And I really should be checking these because it's very important that these actually are correct. Let me check here. Derivative, what do we have? -1 over 1 plus x squared. No, not that power. Yeah, so this is right. So how do we want to do this? So we really should have started with 1/2 here.
Uh-huh.
And that would have been -1/2, and then it would have gotten us to 1. And that's really important because you got to know what you're starting with. Like, do you see the progression? Like this is f of x, this is f prime of x, this is f double prime of x.
Uh-huh. Yep.
Okay, so f of x we can write as it's 1/2 sigma x went to minus x, so it's minus x to the n. So this thing right here, its power series representation is this down here. Is that okay?
Yes.
Okay, so now we got to take a derivative of it to get this one. So we don't even care what's in this line above here. We don't care at all. We just know we got to take a derivative of this sigma thing.
All
So
right.
it's 1/2 sigma n minus x to the n minus 1 times -1. And maybe we simplify that a little bit here. We put maybe bring the minus out. I don't know. It doesn't really matter. It cannot go inside parentheses. You cannot cancel with that. But then we got to take another derivative. Okay, so it's just power rule. I know it's n's, but it's just power rule. It's 1/2. Okay, so we have this minus n times n minus 1 minus x to the n minus 2 now because we subtract 1 from the exponent. Chain rule -1 on the inside. And that we probably would go with this one right here. So we'd make this 1/2 sigma n times n minus 1. You could distribute, doesn't really matter. Something like that. What do you think about all that, if anything?
I don't know. It's just like knowing when to do all this.
Yes. It's I mean, you probably notice how much I was struggling to come up with another example problem once we were doing this. It's because there's only so many that you can start with. Like they have to be derivatives literally of like this. Like you can't, it's going to be a squared or it's going to be a cubed or it's going to be something to kind of get you to that.
Yeah.
I mean, let's look at like, let's say I start with, go ahead.
So if it's 1/1 plus or minus x, whatever, to a power.
Yes.
That's probably when to use.
Yes.
Okay.
Yes. But this one's like a more, I don't know. It's like this isn't that big of a change, but when I take the derivative of this, it's -1 minus x squared to the -2 times -2x. And so you end up getting, I'm all over the place here. You get 2x over 1 minus x squared squared. And it all came from this. So because there's a power in the bottom, that tells you like it's a power series. It's probably a derivative of a power series. This one has a power series of well, x goes to x squared. So it's x squared to the n. So this becomes sigma x to the 2n. And so the derivative of this is going to work with this one on the right. So our derivative is sigma 2n x to the 2n minus 1. And that's what the representation of that. So it's like you have to recognize that like the derivative, the change in the derivative of something gets like, you're going to be given this. You're going to be given what's in green here. This is what's given in your problem. And you're supposed to somehow realize that it came from this.
Uh-huh.
So then you create the power series for the original one, because you somehow know that the derivative gets you to this, and then you take the derivative of the power series to get to the one you want.
Okay. Now, what are we talking about doing like the integral?
Yeah, we need to do those next. So let's just go back to the base power series that you know. Sigma x to the n is 1 over 1 minus x. Okay. And if I asked you to integrate 1 over 1 minus x dx, you know how to do this. It's natural log absolute value 1 minus x. Just let that either sink in, or like take the derivative of this and like confirm that it goes back to that. Because it's really important for us to do.
So why are we integrating?
So you're going to be given a problem. This is what you're going to be given. It's like you're given this intermediate. So this is what you're going to be given.
Okay.
And you are supposed to realize that it is the integral of this. And since you know it's the integral of this, and you know that you can integrate the x to the n.
Okay.
So this becomes sigma x to the n plus 1 over n plus 1 is minus natural log absolute value 1 minus x.
Or where's the n plus 1 because it's integrated?
Integration, yeah.
Okay.
And your instructor may have made a mention that you can switch sigmas and integrals. It feels like a bit of magic, but that is allowed.
So like, what's the answer here?
This on the left.
Okay.
You're given this on the right. You're supposed to know that it came from this, and it's an integral of that. Then you have to know the power series that you started with, and then know to integrate the power series.
Huh. That don't sound fun.
No, I mean, I don't know. I mean, there's all these, it's kind of like you're over here in a room, and you know what's in the room, and you need to and your friend's over here, he's also in a room, and you kind of like are talking to each other. And like the way you get out is like, once you realize what you came from, he does something and you do something, and you get to the same place.
Yeah.
The key. But there's this like, I don't know, curtain wall. Like, I mean, you're solving this is your answer, which has nothing to do with this, apparently,
Yeah.
but that is, that is the case.
Uh-huh.
So like, that's why it's hard for me to make these up, because like this is what I start with, because I would integrate this and then tell you what this is, what you're going to be given.
Uh-huh.
But we can probably find one in your book here to look at. All right. These are horrible. Yeah. And then radius of convergence. I mean, we didn't really emphasize in the last few problems of the same thing. You figure out if that x changed at all, which it didn't in this one. It did in the one I just gave you. So you still have to set that less than 1. When you're doing it, you would have set, like in this previous problem here, you would have set the absolute value of x squared less than 1, but it doesn't affect your radius. Okay, let's look at 15.
Right.
15 is kind of that, it's that same style. Maybe seeing one more of these will help your understanding. Thankfully, this isn't the whole chapter 8. Like, you moved to Taylor series.
Yeah, I get Taylor series and all that. We did that yesterday.
Yeah, so I keep mentioning, like, you're given this, and you're supposed to be like, okay,
Right.
why do I care? Well, what did it come from? What is so one path is to literally just take a derivative. So what is the derivative of this? It's 1 over 5 minus x times minus 1. and that's minus 1 over 5 minus x. And you're supposed to be like, oh, that kind of looks like 1 over 1 minus x.
Right.
That's what you're supposed to realize. You're like, oh, okay. Well, how do I make the powers, since I know the derivative of ln becomes that of this thing.
Uh-huh.
If I can figure out the power series that made this thing, I can integrate the power series to get, because the integral of minus 1 over 5 minus x gets me back here. So if I can figure out the power series of this, I can integrate it to get the power series for this ln.
Mm-hmm.
Maybe it's still not clear.
I see the pattern in it.
Okay, so now you got to find the power series of this. This is minus 1/5 times 1 over 1 minus x over 5. Okay, like that. And so you're like, okay, x goes to x over 5. Just going to change our interval of convergence. And so because we know this is sigma x to the n, we have to modify here. This is minus 1/5 sigma x to the 5th over n. Okay, and then you want to integrate this thing right here.
Uh-huh.
So one of the mistakes here is to think that this 5 is important. It's really, I mean, this is why I often separate it. It's x to the n, and it's 1 over 5 to the n. You got a minus 1/5 here. What's this? Like, you're integrating with respect to x, not the 5 or not the n. It's x is your variable, n is irrelevant. So you're really just integrating this. So it's x to the n plus 1 over n plus 1. And then you have this 1 over 5 to the n, and then minus 1 over 5. You still have this sigma here.
Mm-hmm.
So don't like overdo it. Like don't overcomplicate it. You're still only integrating with respect to x, not n.
Right. I definitely understand this stuff better now.
Good.
That's good.
I mean, like, we're moving into the course trend where it's like you got to do more problems on your own because I can't cover all of the examples.
Right.
And at a minimum, I would recommend going through every example we did, either from the notes or from the video, because you got to go through the steps here until you believe you can do it on the test, the real performance. If you ever done yoga, they say it's practice. I don't know what they're practicing for, but in math, you're practicing for a test or a quiz. And that's what you got going on here. Probably got enough time to kind of start or talk about another problem if you would like. The grouping 15 through 20 look like mostly derivatives, not integrals, although 16 is an integral. So we can maybe look at that.
So, okay. So if it's 1 over 1 minus x squared, for example.
Yes.
That's when you would integrate. If the problem looks.
You meant like this, right? This.
Yeah.
Yes. Yeah. Instead, you would actually want to integrate this and like see what it goes back to, and hopefully it's not too wonky to do that. I mean, it's
and then the natural log 1 minus x, for example, that's when you would take derivative.
Yes.
Okay.
You're always trying to get back to this place, whether you take a derivative to get back there or an integral to get back there. And hopefully it's only one time.
Yeah. Okay, that makes okay. Okay. All righty. We could be done.
Okay. The internet's available for some of these if you need, worked out solutions that I didn't do today. So keep that in mind.
Now, you helped a lot today.
Awesome. Well, thanks so much. I'll send you the notes and the screen recording here shortly, and I'll see you next time.
All righty. Thank you.
Have a great day.